last time, we were discussing how, I guess conceptually, how you can think of resistances. And I left you about thinking about the length of the road, or if you prefer, just like experimentally with straws, the length of the longer the straw, the harder it is to breathe. Right? Did you go and find a coffee stirrer and walk around with a coffee stirrer? Did you try this? No? Well, you should try it at least once. I mean, it is ridiculously hard to breathe. Like, it's weird. So the length of the straw, the harder it will be to breathe through the straw. Or if you think about the length of the traffic jam, the harder it is to get from point A to point B. So as the length increases, you can think of the resistance increasing. Okay? Similarly, if you increase the area, you are giving more options to move around any impedances or any things that are in your way, and therefore the resistance goes down. You can move easier. This would be, it's easier to breathe through a larger straw. And so heuristically, you can come up with this relationship that the resistance is proportional to L and inversely proportional to A. Now, of course, you could think of air moving through a tube. You could think of cars on a highway. In reality, we're thinking of electrons moving through a wire. And the physical resistance, I believe the origin of the actual resistance is as an electron moves through the wire, it sees electron clouds of the atoms that make up the wire. Okay. And of course, as it's trying to move through, if it sees an electron cloud, that's going to slow down the electron. Right? It sees a cloud, your Coulomb force will slow down that electron, and it somehow has to navigate around the electron cloud associated with that copper atom. But then next in line is another copper atom, for example. And so the electron that's trying to move through the wire has to navigate around that copper atom, and so on and so forth. So that's, again, why the larger area gives this electron more maneuverability left, right, up, and down to navigate around these copper atoms, for example. Whatever material the wire's made out of. Same thing, that's why the length of the wire increases the resistance. It's because you have more things that you have to get around as you move down the wire. So the last thing, this Greek letter rho, is a material property, and I apologize. I don't know who came up with it. It kind of stinks, but that's life. R is the resistance of an object. Rho is the resistivity. So the resistivity is a material property. We go to a table, whether it be in your textbook or in, what is it? Do you guys still use like what, the CCR manual? Is it the CCR? That big chemistry textbook? I'll have to look it up. I think we have one up in the physics lab. Just like, yeah, I know that in chemistry, you used to, instead of Googling it, you'd have to actually go to this manual, which is probably like 2,000 pages. And it's just different chemical and material properties of every element. And, a lot of common organic molecules or inorganic, like you just had to, oh, I need this value, and you just go to the book and look it up. Okay. So this would be, you got to go to a book and look it up. Just to give you an idea, I put copper and iron in here, which have really low resistivities. And you notice this is 10 to the negative 8. And I don't remember the range, but if you go to an insulator would have a very high resistivity. It might be on the order of 10 to the negative third, or maybe even it depends on what material, but it could be very high, and maybe even on the order of 1. I don't remember for sure. But your text, I can't compete with Google on that one. I never bothered memorizing them or even getting an idea, because you just look them up in the book and then so. I think I left you there. Yeah, okay. Blank page? Can I put a blank page in? Yes, blank page. All right. So let's get an idea. Let's play the same song and dance. Conceptually, we have two scenarios where you could have something like series and you could have parallel. And now I'm thinking, we did this with capacitors, but I wanted to just go through and do it with resistors as well. If you have two resistors in series, well, first of all, I should ask you, what does series mean again? When you have two items, circuit elements in series, what does that really mean?
It's like the distance increases.
Okay, you can think of the physical length of the object or the distance increasing, okay? But what does series mean? I mean, I agree, that'll be the end application, the practical side of it.
It's one after another.
One after another, right? To get, for example, if we were talking about capacitors, to get to the second capacitor, you have to go through, I'll put that in air quotes, go through the first. And you have to get to the second capacitor, you have no choice but to arrive at the first capacitor. There is one and only one option. Similarly, we'll think of resistors. To get to the second resistor, say R2, you must first go through R1. And now, unlike capacitors, I can literally say, without air quotes, go through. Because resistors don't collect any charge, they allow charge to pass through. And so if you want a charge to get to resistor 2, it first must traverse through resistor 1. Oh, yeah, okay. Well, what does this effectively do? If I'm thinking about having two resistors in series, and I would rather replace it with a single equivalent resistor, say Req, having two resistors in series, what does that essentially do to, for lack of a better word, the length of the traffic jam? If I put them in series, makes it longer, right? If I put two resistors in series, that's like making the traffic jam longer. There's a longer length of road that the electron has to navigate in order to get from point A to point B. So putting these in series essentially increases, sorry, man, why do I bother writing? Increases the length of the road, increases out. Which means what happens to the overall resistance? If I want to take these two resistors in series and I want to combine it into an equivalent resistance, conceptually that's making the road longer. What happens to the overall resistance, the equivalent resistance? It's R1 plus R2. You take the length of 1, you take the length of 2, I'll say air quotes again. And so what happens here is that you get that the equivalent resistance is simply the sum of the two resistors in series, like increasing out. Yay, nay? Beating a dead horse? No. Well, how about parallel? What does parallel circuit elements mean again?
An option to go.
Yeah, you've got an option. I'm sorry?
Increase your lane.
You increase the number of lanes. Yeah, good, you're good. Right? You get some option. I can go through one or the other, but I do not have to go through both. There's a fork in the road. You pick it up. Did I use that one already? Yogi Berra, baseball player. He's credited with all these weird expressions, like, it probably didn't say all of them, but when you see a fork in the road, pick it up. Or baseball is 90% physical and 30% mental. I'm trying to remember the other ones. Do you know any more?
I just know that 90%, 50% physical, mental one.
Yeah, I mean, I don't know the specific numbers, but the whole thing goes through like, 90 plus 30 is more than 100, like, it's, okay. Yeah. Yeah, so you got a fork in the road. That means that you're essentially, from an effectively, you are changing the number of lanes. You're increasing the number of lanes. You're increasing the area. And so if you increase the number of lanes, the overall resistance decreases. If I want to take these two resistors and replace it with a single resistor, Req, this resistor value will be less than either of those, if I will. I think it's actually, okay, well, yeah. So this is effectively increasing. Why do I bother? You guys know what I'm saying. Okay, increasing A. A goes up. And so for resistors in parallel, you can think of the equivalent resistance is given by the sum of the individual resistors when added in inverse. And again, I know I had this on Wednesday. That is exactly the opposite relationship of capacitors. Which is why I say think about kind of the underlying physical thing, and that will tell you what happens. Right? I don't remember these. I just remember when I put them in series, the road's longer, so I should add the resistors. When I put the capacitors in parallel, the area gets larger, I should just add them. So I don't memorize like parallel and, I think of kind of more what's going on. Someday I'm going to drop that. I'm just going to, I think I did wreck the tip on this one. They didn't make these Greg proof. So fortunately, at least electrical plugs are Greg proof. Right? There's only one way to plug them in. They didn't do that. I'm waiting for you. Oh, the day and age of USB-C. Oh, can't wait. Doesn't matter. Somehow I have a 50-50 shot and I get it wrong 100% of the time. From a statistical point of view, I know this is impossible, but I still seem to be able to do it. Okay, questions? So of course, this is the exact opposite kind of relationship that you see with capacitors, which means it's the exact opposite kind of relationship you would see with springs as well. And so I said, hey, springs and series in parallel follow the same kind of idea. Capacitors in parallel kind of follow the same idea. Resistors in parallel and series are the opposite idea. I'm trying to think of where else you would see this. I think batteries kind of follow along with resistors. I think inductors kind of go along with capacitor. I gotta double check. No, inductors are gonna follow this as well. So you could kind of apply this, you can extrapolate this to other circuit elements as well. That's all I have to say about that. I put in a bunch of extra blank slides. Get an idea here. I just thought I'd throw this one up. If you actually if you ever need to, first of all, hi, my name is Greg, and I'm scared of doing electrical work at my house. I know all the basics. I'm still scared to do electrical work. Like, I know I should be able to like replace a circuit or wire up a light, but I'm just waiting for the day where I screw it up, and then you'll say, okay, well, Greg was a fine professor, but he didn't know his electrical stuff. Okay. In any case, I put this up here because with household electronics or wiring, they have something that's called gauges. Okay. So that's the technique. If you go to Lowe's and you say, I need some wire, they're going to say, what gauge of wire do you need? So I thought, well, I'll at least put this up because you'll run across it every once in a while. So I have zero idea why, but gauges run in numbers from 10 to 28. The larger the number, the smaller the cross-sectional area. Again, I have zero idea why they do that. I don't know somebody will have to tell me someday why they do that. I don't know. Okay, so, but each specific gauge, so you go into Lowe's and they say, oh yeah, we'll give you some 10 gauge wire. That corresponds to a particular, I think this is a diameter. So that will refer to a specific diameter, and so on and so forth, all the way down to gauge 28. So I just thought, okay, well, what happens if you have, let's say, the resistance? You got 3.2 meter wire of 18 gauge. So go ahead, take a minute, calculate out what's the resistance of a 3.2 meter long wire that's 18 gauge copper. Okay. Talk to your neighbor, go at it. Yeah, let's assume that this is a diameter, not a radius. So I'll highlight that as well. We're just gonna get a cup of lukewarm coffee going here. I think 18 gauge is standard electrical in a house, if I recall correctly. Probably not what we have in the walls here. Okay. Yeah.
This area, like cross-sectional area, at few meters.
That's a good question. Does cross-sectional area have to be meters or millimeters? What are the units of the resistance? Meters. So if you're going to do it, you want to use that value, then you're going to want to make sure you have your meters. Ah, that's right. Okay. I'll be right back. Right back. Right back. It's so sad. He's such a loopy little race. Oh, look at that. See, there's good product. See, that's better.
Bigger doesn't get better.
Oh, yeah, it does, right? A high polymer pentel eraser, this is world class. Oh, but this is a bigger one.
I mean, I'll take it.
I ordered 10 of them and I only needed 2, so that's fine.
How's your chalk?
Love it. I shared some with Dr. Katzoff. I think he's up too.
Okay.
Yeah. But he apparently told me it tastes good, which worries me just a little bit.
What?
Huh?
What? He said it tastes
He
good.
said it tasted good, so that worries me just a little bit.
You shouldn't give him any chalk.
Well, he's gonna eat it up either way.
Yeah.
The cross-sectional area of the wire. So essentially, what you want is you want the area of that circle.
Okay.
Yeah. Okay. And in fact, maybe I should be more specific. Yeah, so I said that area is the cross-sectional area. Another way to think about it is whichever way the current flows, you want to take a slice perpendicular to it. So the current, if you're using this wire, the current's going to be flowing through the wire. The area that you need is when you cut perpendicular to the flow of the current. So if you ever catch yourself playing with something like graphene or, like some sort of carbon nanotube, that's important. So like the flow of graphene in the plane is different than the cross plane. I think it's graphene, right? Yeah. So you take a thin layer of graphite and the resistance in this direction is vastly different than the resistance in that direction. If you run it in the plane, it's low resistance, but if you run it cross plane, it's high resistance. So it's very weird thinking that, you know, it's a crystal, is it crystal structure? No, graphene's not. You know how graphene was discovered, right? No? They literally took a chunk of coal, put a piece of tape on it, ripped the tape off, and that was their sample. That's how graphene was discovered.
Of graphene?
Graphene, single layer of graphite?
Oh, not like graphene.
No. Oh yeah, the material. Yeah, the material. Yeah, they took some graphite, they put a piece of tape on it, ripped the tape off, and that removed a single layer of the graphite, and that's how they discovered like the material. That's how they would prep their samples to examine graphene. It's this two-dimensional graphite plane, and so they has some weird properties. It's very strong. It's the only thing to get, I think it's the only thing to get an Ig Nobel Prize and then a Nobel Prize. Ig Nobel? You ever heard of these? Okay, finish your calculation, then I can tell you the Ig Nobel Prize. Yeah, finish your calculation first. Sorry, that's off topic. We should stay focused. Stay on target. Yeah, right, I mean, if you get a really large value, then or let's see. If you get like a ridiculously small value, then, yeah, if you get a ridiculously small value, then you might have some problems. I mean, it shouldn't be like, 10 to the negative 10th or anything. Yeah.
Are those millimeters or?
Oh, that's bad. Man, where did I pull that from? It's supposed to be millimeters, yeah. Not mega something. Yeah, no, it's supposed to be millimeters. Yeah, excuse me. Yeah, I never even noticed that. So apparently the source that I shamelessly stole this from, learnsparkfun.com tutorials working with wire thickness. Apparently, no, this is supposed to be millimeters. Yeah. Well, I guess you could say megameters. It's just a million meters. You got it? You got some idea? I mean, what's that? I think I was running 1/10, I think it's 0.06. Is that about what you got? Does everybody know you got yay, nay?
Right.
So yay? Ballpark? Point?
Ohm, right?
Oh, I'm sorry?
Like the omega.
Yeah. So you get an area, let's see here. So the radius is something like 0.5 millimeters. So that's 5 to the 10 to the negative third. Okay, so if you want the area, that's, you got to square that and multiply by pi. So squaring that, you get 25. And then 10 to the negative 6. Oh, except this is a point. Oh, you should yell at me. It should be a 4, right? 0.5 millimeters, that's 5 times 10 to the 4th. So if I square that, I should get something like 10 to the negative 8. And so that's the area multiplied by pi. So, okay, so my resistance is the resistivity times the length over the area. So I get something like 1.6 times this 3.2, and I've got the 10 to the 8th out here, -8, divided by, we'll just round this to 75, 10 to the -8. So 25 times 3, thinking pi r squared, so r squared was 25, and I'll just multiply by 3 for pi. And so we get something like that, okay, cancels. 1.6 times 3.2, ballpark. Just ballpark it. 5. 3 times 1.6 is 48. Oh, okay, all right. 3 times 1.6 is 4.8. So let's just round to 5 and call it good. I'm just doing this in my head. You guys have your calculator, but you can ballpark it. So this is something like 5 divided by 75. So what is that? 5 divided by 15. So something like 1/15. 1/15 of an ohm. 0.06? 15 divided by 6, or 15 times 6 is 60 plus 30, which is almost a 1. Okay, let's say about 0.062. You guys are staring at me like I'm crazy. This is what you did, right? Okay. No? Yes? No. So you get a 3-meter wire. I mean, this is why copper is so nice. You get a 3-meter wire, and it has a resistance of almost 6/100th of an ohm. You need a really long copper wire to get a really high resistance, I guess is the other way to say it, right? Okay, Ig Nobel Prize. You've heard of the Ig Nobel Prizes? Well, mental break for a second. Yeah. It's an award given annually to research that seems completely ridiculous. All right, so Ig Nobel, IG Nobel. Where'd my cursor go? There it is. I think it's Ig Nobel Prizes. So I think yeah, there we go. So what's one of them? Oh, the coefficient of, there's something about, one of them that won the prize was, are banana peels really the slipperiest? And so it was research studying the coefficient of friction of banana peels as compared to other fruits. Indeed, they found it was. Or it was one of the slipperiest. I think the slipperiest was like the tangerine peel, which seems something, yeah, I have to go back and look. I forgot the research already. One of them was, what was another one? It had something to do with sheep shearing. I think it was something like the coefficient of friction of unsheared sheep on different inclines. So that one got one. But one of them was graphene. So it got an Ig Nobel Prize simply because you take graphite, you put Scotch tape on it, you rip it off, and there's your graphene sample. So it got an Ig Nobel Prize. You know, I can't remember what it was, like the material properties of one-dimensional graphite. And I don't know why that would get an Ig Nobel Prize, but then a couple of years later, it got a Nobel Prize because people figured out, oh, this stuff is actually really interesting. So one of the things that's interesting about it is that it has very low resistivity. If this is a single layer of graphite called graphene, it's very interesting because if you send an electrical signal this way, it's very conductive, low resistivity. But if you try to send it this way, it's high resistivity. So the direction that you send the current actually, which is very weird, because usually when you increase the area, usually the resistance goes down. Graphene, excuse me, one two-dimensional stuff acts very differently than three-dimensional. It's really weird. I don't understand it. Okay. There's some other really interesting material properties in terms of strength and all that kind of other stuff. Okay. Oh yeah, mental break. Jokes? Yeah, you like jokes? Oh, jokes.
this a joke?
Yeah, this is the joke. It's a visual joke, right? We can't all be verbal, right? No? Ohm away from ohm? Oh, see, now you're laughing. Oh, okay. Yeah, how about, of course, you have this one. You can impress your friends this evening at, well, I don't know what goes on. Not at all. You're not interested in mobile ohms? Okay. One last one. We'll try. Maybe we could go for two, but okay. Here we go. This one will be a crowd pleaser. There we go. I can feel it already. There we go. This nice. And yeah, I'll put this on. Do that. There we go. And the coup de grace. You know, ohm on the range. No? Maybe physics strips aren't our thing. Okay, I got you. That's okay. Yeah. Computer science jokes? There are 10 types of people in this world. Those who know binary and those who don't. No? Yeah. 1 0 in binary is 2. So there's 10 types of people in this world, those who know binary and those who don't. No? Because if you know binary, then 10 is 2, and then it makes sense. But if you don't know binary, then no? You're shaking your head. Is that a terrible joke, or I get it? No? Yeah, counting in binary is weird, right? You go 0, 1, and then it's, yeah, so 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, et cetera, et cetera. So every time you hit 2, you go over the next digit. So in our base 10 system, when you count, you get to 9, and then when you hit 10, you have to go over another digit. And then you get to 99, and then you hit 100, you go over another digit. So it's called a base 10 system. Binary is a base 2 system. So when you hit 2, you have to go over another digit. So if you're counting, you start off with 0, then you go to 1, then the next number would be 2, so you shift over 1 digit. Then the next number would be 3, and the next number is 4, which means you have to shift over a digit again. 2 squared. So then you shift over another digit, and then you keep going. So you go with yada. Completely beyond the scope of this course. But it's interesting to think about, like base 10, every time you hit a power of 10, I should say 10. Every time you hit a power of 10, you shift over a digit. So this is the same thing, it's just when you hit a power of 2, you have to shift over a digit. So the next time is 0, this is 2 to the third, otherwise known as 8, et cetera, et cetera. Okay, I can see okay, I can see you want to go back to resistances instead. Okay.
Was physics your only major?
No.
It's very smart.
Oh, no, yeah, this is just kind of, that's the only stuff I know about binary. If you ask me to program in binary, like forget it, I don't know what's going on anymore. No, I had a couple of majors, so.
What were they?
Physics and French and math. So, but it took me 5 years, so. And it's hard not to get a French major when you spend a year abroad, so I kind of just ended up with a math major because I had nothing else to do with my last semester, so. Math is boring. Those guys are worried about things like, does this solution exist? Yeah. Let's do something fun with it. Okay. Survey says, which arrangement gives you the largest possible resistance? Rank them. You can rank them too. Yeah, why not? Go ahead and rank them. If you can tell me the largest, you can tell me the smallest. If you can tell me the smallest, you can rank them. So just rank them. Watch Mark Rober. Just watch like Mark Rober or something. Oh, he's a YouTube guy, NASA engineer. Started a YouTube channel. Watch the squirrel one.
Okay.
If it doesn't make you laugh, if Fat Gus doesn't make you laugh, nothing ever will. Okay? So Fat Gus will make you laugh.
Okay.
Okay, I'm sorry?
I was like, this one.
Oh, you mean the copper wire one was no bueno?
No, just fine.
Oh, okay.
Last class.
It takes a little while.
Yeah.
Yeah. But if you don't, that's always the thing, like, the first time you see it, it's always hard. So, like, I mean, vectors, the same thing. Why do we give you vectors in chapter 1 of 161? It's because you really need to know them by the time you hit chapter 5 or 6. But if we wait until chapter 5 or 6 to give it to you, then all that time that you kind of had to get adjusted to it and acclimated to it just disappears, right? So, same thing, hopefully.
Yeah.
Yeah. Got it? Survey says, highest resistance, the one in series, yeah, so we'll say the one on the far right, then next highest is, I'm sorry? The individual resistor, right, there's only one cap, and then the lowest is 2. And in fact, if all of these resistors are exactly the same, which is the underlying assumption, no, I'm sorry, I say it right there. You can, well, this is a resistance of all. What's the overall resistance of this arrangement? 2R. And how about this arrangement? 1, oh yeah, that's a good, we should double check that, right? Yeah, this is in parallel, so I'll say the equivalent resistance is the sum of the individual resistors added in inverse. Now, be careful. Right now, I said all the resistors are the same. Please be careful if they're different. Okay? Because, and I'll say that, let's say if they are different, I say please be careful because, and I know I'm not talking to you, I'm talking to your friend that's not here right now. Okay? Like, you know, and not even the online people, they count as being here. I'm talking about, you know, the friends that aren't here that'll take physics later. Okay? One of the temptations is to say this. Okay? Please be careful. That's not, yeah, right? That's not right. Right? Before you add them together, you need to common denominator, okay? So just be careful. I'm not warning you, I'm warning your friends when you're helping them, okay? And let's be honest, some weird things happen at 2 o'clock in the morning when you're doing physics. Physics is not meant to be done at 2 o'clock in the morning if you can avoid it, okay? You find the most uncomfortable chair in the coldest room possible and coldest and brightest room possible, okay? That's the time to do physics. So 10 o'clock in the morning in the brightest room, that's the coldest that you can make it and the most uncomfortable chair. Okay? If you don't do that, I guarantee you, if you get a comfortable chair in a warm room and you're doing physics at 9 o'clock in the evening, right, yeah, you're gonna fall asleep. I fall asleep doing it, okay? I know you're gonna fall asleep doing it, okay? I'll wake up, there's gonna be a drool stain on my pillow, my physics book is on the floor, and I'm like, what happened? Okay? Maybe not exactly like that, but you get what I'm saying, okay? Find a bright room, make yourself uncomfortable, and then do physics. Make sure you're awake. Okay? So no, this is not right. This is not the way to do it. You have to find a common denominator first. Okay? So say if I have two different values, common denominator means that I've got to do something like this. Something like that. Right? Multiply the first one by R2 over R2. Multiply the second one by R1 over R1. Now I get R1 and R2 in the denominator, and I just take R1 plus R2 in the numerator. But unfortunately, you're not done yet. And here's the second place where I always forget. This is not your final answer. Right? Because over here, look, I've got 1 over REQ. Right? So that's where I fail usually, is I'll do the common denominator right, and I'll say, oh, okay, here's my final answer, right there. Oh, nay, nay, nay. Don't forget that you have to take the inverse of that. REQ, right? You have 1 over REQ equals this. So I've got to flip both of those. And something like that. Now we're good. So sorry, I said, okay, let's assume they're the same, and then I did the derivation like they were different. But now let's go ahead and say that R1 is equal to R2. If I put in, if R1 and R2 are the same, the numerator gives me R squared. The denominator gives me 2R. And so my overall resistance is not 1 over 2R. It is R divided by 2. We'll put R over 2 here. Third warning. So first warning, don't forget the common denominator. Second warning, when you get to the end, don't forget that that's 1 over R equivalent, so you got to take the inverse. The third warning is this is a very nifty shortcut. Be careful with it. If you have 6 resistors all in parallel and all of the same value, you can just take the resistance and divide by 6. Or if I have 2 resistors that are exactly the same, and I want to know the equivalent resistance, it's just the resistor divided by 2. Or if I did 3, it would be the resistor divided by 3, et cetera, et cetera. That only works if they're the same resistor. Okay. This approach, adding the inverses and then taking the inverse will always work. Okay. But if you say, well, they're the same resistors and they're all in parallel, then I can then this only works if the resistors are all the same. Okay. So that's the third warning, is that, and I think in lab, if I recall correctly, I see this a lot, you'll do a resistor lab where all the resistors are the same. And so you'll find yourself kind of using this rule a lot. And then I'll ask a test question where they're different. And I'll see people say, oh yeah, just take the resistor and divide by 2. I go, no, they're different resistors. You can't do that. How would you know to choose that resistor instead of this resistor? So just be careful. Okay? The general warning would be, you can use that, that's okay, but use it with caution. This is the better way to go. This one will always get you the right answer, regardless if they're the same resistors or not. Okay? So just be mindful of that. I do it too, right? Like I say, oh, I'm not going to go through the whole thing. I know it's R over 2 all day. So just be aware, this is only a specific, very small subset of questions. And that should be, you probably run across this, right? Before you deploy an equation, you should ask yourself, under what conditions is this equation useful? Under what conditions is it valid? And hopefully, when you get into your future careers, you'll see somebody else use an equation that they shouldn't have used, and you'll say, not constant acceleration. Don't use the kinematic equations. Okay. We'll say, thank you, you just saved me a $2.7 billion rover. We did it! You saw that yesterday? Yeah, you guys should be excited about this, right? Perseverance rover landed yesterday. $2.7 billion rover finally landed on Mars. One scientific mission to examine if life existed on Mars. You know? Also has a sample return mission. It's supposed to actually dig some holes and take some samples and bottle them up and then leave them behind for another rover to pick up sometime in the future and return them to Earth. I just like thinking about this little rover that's just picking up samples, bottling them, and then just shooting them out the behind. And just little breadcrumbs. I think NASA called it something a little less, they call it breadcrumbs. We can call it rover excrement. Okay, questions? So that's one way that you can combine these capacitors and or resistors. So I should also give you the relationship between a change in potential and a resistor. So for capacitors, the relationship was this. We defined the capacitance as being the charge on the capacitor divided by the potential difference between the capacitor plates. If you want, you could rearrange that definition and say that the potential drop across the capacitor is given by the charge of the capacitor divided by C. I think I mentioned this. You can think of the capacitance as giving you a constant of proportionality between the charge on the capacitor and the potential drop across the capacitor. Okay. A resistor has a similar expression, modified ever so slightly. So I put it up here, and I have no idea why we don't have like a different phrase for the capacitor. This capacitor thing, it's not like you call it like Gregg's law or Gregg's astonishingly intuitive law of capacitors. Or something, I don't know, we don't do. But for resistors, we do. For resistors, it's called Ohm's law. And I'll walk you through this. We have a potential drop across a resistor, that's again this delta V, is given by the resistance and I. And I apologize, I look at it now and I don't I use capital I here. Does the book use capital I? Some books use, okay, so as a warning, some books will use capital I, some books will use lowercase I. I is a special thing. It's a change in Q over a change in time, otherwise known as charge per unit time. So, current, yeah. So this I is charge per unit time, it's current. Yeah. Oh yeah. Oh, do I have it here? Oh, I hope so. Okay, change in electric, so current flowing through the resistor. Okay, we got that. Okay. I think I just remembered. I think I remember what I have here. Okay. So you can imagine, I mean, one way to think about current is that you're sitting on the side of the wire and you're just counting how many charges pass you. You look at your watch and say, okay, starting now, and you just start counting. Kind of reminds me of this, right? Like, okay, yeah. No volume. Oh. We have to start that again, right? Right? You're sitting on the side of the wire, you just walk, you say, oh, -1, -1, -1. You sit there on the side and you just watch these charges go by. And if you count how many of these charges go by and you know how long you have been counting for, you can determine the current. So it's the number of charge, if you will, I use delta Q. What I mean is the number of charges that pass you divided by how long you were counting for. And those two numbers can be used to get your current, the charge per unit time. You've seen Ohm's law? You've seen this before? No? Okay. Well, then it's going to put it up there. So what the resistor does, a different way to think about resistance, is that resistance is the constant of proportionality between an applied potential and the resulting current. If I take a copper wire that's 3.2 meters long with a gauge 18, and I apply some constant potential difference across the endpoints, knowing the resistance, you can automatically tell me what the current is. Okay. We got, what do we have? We had, yeah, if we're talking about that copper wire, I don't know, what's your favorite potential difference? 9 volts? Okay. Let's say we we take this 3.2 meter long 18 gauge copper wire that has a resistance of, we said what, 0.06 ohms, and we hook it up to a 9-volt battery. Let's say we hook it up to a 9-volt battery. One end is at 0 volts, the other end's at 9. How much current runs through that wire? Well, you just, okay, we plug that stuff in. So we get 9 volts divided by 0.06 ohms. That will tell me how much current's running through the wire, which is a wicked lot. Right? Let's see, we got to scoot over. Let's scoot that decimal place over too. So we can do that to the numerator. Yeah. Right, yeah. We scoot the decimal place over 2 in the denominator. We can do it in the numerator as well. Yeah, we just multiply both top and bottom by 100. Hi, my name's Greg. I swear I had a math major at one point. They took it away from me because I couldn't. Yeah, okay. So what, we have 900 divided by 6. So that's 100, remainder of 300, 150. Okay. So 150 equals I. Quick, what's current measured in? Or you could look at this over here and get an idea. The unit of charge. Coulomb. Unit of time is seconds. So a current is a coulomb per second. Now, usually you won't see it like that. Coulomb per second is kind of, if you take it down to the most basic units possible. Most people won't do that. They'll just say it's amps. So you'll see, you can use an uppercase A for amps, or you could say coulomb per second. It's defined as an amp. Actually, I guess that's probably an abbreviation. It's probably named after ampere. So I should probably give credit to where credit is due. I think there's an accent aigu there. Excuse me, I think that's an accent grave. Goes down. Any French speakers, francophones? I don't know if they use them in Spanish or not. I don't know if they use them in German. In fact, I have no idea about any other language except French. Okay, so there's no francophone, so I can just call it whatever I want. You guys can't contradict me. Okay, good. Right? You ever notice that? Sometimes we're obsessed with getting the details right. Like, oh, my first car out was blue. Oh, no, wait, maybe it was teal. I'm like, I don't care. You could lie to me and I won't tell you. I don't care. I mean, it's not that I don't care. It's just it's not important, right? The details are important. Okay, so this is in amps, 1.5 amps, or excuse me, 150 amps. That's actually, that's a lot, right? Like, current that your heart uses to beat is on the order of milliamps. Hundreds of milliamps, I think, are the electrical signals that run through your heart to kind of keep it going. So if you run 1.5 amps through your heart, Like, that'll swamp the signal that's actually controlling your heart, and then you have problems. Right? Now, fortunately, if you hook this up to a 9-volt battery, you go, holy cow, that's enough to really hurt you seriously. Yes. Now, there's a physical limitation in the sense of there's a finite amount of charge that the battery can provide. Okay? The battery is not an infinite supplier of current or infinite supplier of charge. And there's still a finite amount of charge overall that battery can provide. It'll provide all it can as fast as possible. Okay? But my guess is you hook up this wire to the battery, it's gonna like deplete like in a couple of minutes, tops. And that's really all I have to say about that. Yeah, your heart runs off of like tens of milliamps. Incidentally, if you ever find yourself working on something electrical, I don't know if one of the things is you put a rubber mat underneath you, right? Because rubber is a good insulator, okay? So it tries to prevent you from touching the ground where electrons tend to like to go, if they can. Okay? The second thing that you always make sure you do is you work one-handed. Why would you work one-handed? It tends to be your right hand, basically because you're right-handed, but also there's an advantage. Most people are right-handed. There's also an advantage because your heart is on your left side. So if you work right-handed and you happen to connect a circuit and become part of the circuit, current's going to run down your hand into your arm on the right side of your body and hopefully through your right foot. The thing that you definitely want to prevent from current running is across your chest, which means you don't work two hands. Because if you accidentally connect the circuit when you're working with both hands, all of a sudden you've got a pathway through your heart. So you'll see people working one-handed, especially if it's on electrical stuff, is because you want to prevent that pathway from passing through your heart. Now, I don't know if you're ever going to find yourself doing this, but it's always, hey, why is that guy working one-handed up there? It'd be easier if you had two. Well, yes, there's a practical reason why, yeah. I don't know, I think there's a problem that asks you to determine the resistance of the human body. I think at some point, I think I give you like the average resistivity and the average, path length across your arms or something. You can incidentally, that also depends a lot on how hot it is. Right, if you end up with sweat on the surface of your skin, your resistivity drops. No? Okay. Right, if you have sweat on your skin, there's a bunch of calcium chloride in that sweat, right? Maybe it's potassium chloride. Table salt. So there's ions in that sweat. Well, if you apply a potential difference, those ions will move and transmit the current along the surface of your skin a lot faster. So you tend to be less resistive when you're sweaty, is because there's these ions in your sweat that kind of move around. You can, you know this, you cannot actually electrocute yourself if you're in pure bath water. Like if you're in, not distilled, what's the word I'm looking for? Deionized. If you are in true deionized water, you should not be able to electrocute yourself. Because the thing that electrocutes you is that those extra ions that are in the water start moving around and transmit the current through the water. Okay. So if it's deionized, if you remove all of the ions, theoretically speaking, you can't electrocute yourself. There's nothing to actually transmit the current, right? We can Groundhog Day it, right? Groundhog Day, Bill Murray. There's a scene where he's in the bathtub and he drops a toaster in. Trying to figure out, have you seen this? That sounds morbid, but it's part of the thing is he keeps really reliving the same day over and over and over again. So he's trying to figure out how to break the cycle. Turns out he has to fall in love. He has to start caring about other people. That's probably what it is. Yeah. You guys okay? I mean, I know it's right. Huh? So that's all I have to say about that. That's Ohm's law. That should be enough to get you through. Okay, yeah. We already did that. Oh yeah, I could ask this. Based on these three arrangements, which resistor has the largest drop in potential across it? Survey says what say the rest of you? I hear a couple equals, I hear a couple middles. I say which set has the largest drop across, maybe I should say across the series of resistors. There we go, maybe that's a better way to say it. Or the grouping, I shouldn't even say series, because series means, one after the other. I should say the grouping of resistors. For which arrangements is the potential drop across the grouping of resistors the largest? Okay, so now I got equal, I've got middle, I've got the third one. Let me ask a different question. Which circuit has the largest battery attached to it? Largest. Survey says they're all the same. Therefore, the potential drop across the grouping of resistors is all the same, right? You actually answered this question already. Replace the resistors with capacitors. Said which grouping of capacitors has the largest potential drop across it? Well, the batteries are all the same, therefore they all have the same potential drop. But you know that something's different. You say, well, I know something's got to be different between these, and I say yes. Say, which of these groupings of resistors has the largest current passing through it? And you would say, well, the largest current corresponds to high resistance or low resistance? Low. So the question would become, the highest current corresponds to the lowest resistance. Which of these has the smallest resistance? The survey says this one, the one on the right. And in fact, you could actually tell me how much more current is flowing through this circuit as compared to that circuit. Survey says what's your gut say? Twice. Yeah. Ohm's law, I'll go back to Ohm's law here. If this delta V's are the same, that means as the resistance increases, the current decreases by the exact same amount. So if I double the resistance, the current has to decrease. It has to be cut in half. Or if I quadruple the resistance, then the current must be a quarter. One goes up, the other one has to go down. And you've probably heard that, right? Follow the path of least resistance. Lower resistance paths will carry more current. You guys okay? Which one? I'm sorry? They are all three the same. Yeah. So for the electric potential one, all three batteries are the same. So the drop from one part of the resistor to the other part is all the same. So if I'm looking at the drop across the grouping of resistors, It's the same for all three because the batteries are the same. The thing that changes is, oh, we could go further. You said highest current, second highest, third highest. Which battery is going to run out first? Which battery is going to die the fastest? Yeah, low current, or excuse me, the high current one means that the battery is using up all of its, quote unquote, stored energy the fastest. So not only do you have the high current, but also that, that battery is going to get replaced faster. As opposed to something here. Momentarily said, oh, did I just say the wrong thing? And I said, no, we did it right. So you know that something's going to change. One is the current's going to actually change. But then also, in addition to that, the higher current battery, the battery that's providing the highest current is actually going to deplete the fastest. Go play in the snow? Yes. We'll pick, that's all I have to say about Ohm's law and resistors. But what we're gonna do next, what we'll do on Monday, is we'll start working with a set of laws, they're called Kirchhoff's laws. So I've given you a way of kind of conceptually combining resistors or conceptually combining capacitors. Kirchhoff's law gives us a more algorithmic approach, a stepwise approach that we can do to analyze circuits. Okay. So more complicated circuits. When you look at a circuit and say, I don't know how to combine these things, are they series, are they parallel? Kirchhoff's law gives us a different approach that will work. Okay? So hey, okay, get out of here. Thanks for your attention. I'll see you Monday.